Okay, hello students, and welcome to our lesson 12, which is on performing volumetric analysis. Today we want to recognise that acid-base titrations rely on the identification of that equivalence point and by measuring the associated changes in pH using chemical indicators, pH meters, to reveal an observable endpoint. And we want to look at appropriate mathematical representations and analyse that experimental data. And so on to calculate moles, mass, volume, concentration from volumetric analysis data. First of all, I just want to have a look at phenolphthalein because that's going to be one which is quite commonly used. And you can see here we're starting off with a strong acid and let's have a look here. Here's a strong acid and here's a weak acid. You can see a slightly different characteristic in the initial slope of each curve, and then we have the buffer zone. The midpoint is pretty well the same for each, but remember a weak acid has that buffer zone, whereas a strong acid will pretty well completely dissociate. And so then we'll have the equivalence point, so we'll have that nice sharp equivalence point. You'll notice that strong acid and strong base, it should be around 7, a weak acid and a strong base will be closer to 9. When we are performing our titration, remember to just keep swirling your solution, and we'll have a look at that in the cracking class, but that's important. And the end point for phenolphthalein is not this dark pink colour, but it's just as it's turning pink, so that's our good end point. Some of the equipment that we'll use, first of all, our volumetric flask is used to prepare a standard solution of, for example, sodium carbonate. It could be a variety of different things. An accurately weighed sample of sodium carbonate is then placed in the flask and dissolved in deionized water to form a specific volume of solution. So remember that specific volume is quite accurately calibrated, generally plus or minus 0.1 of a mil. We have a pipette, and that's used to measure out specific volumes of a solution, for example, of hydrochloric acid. Now, this is called an aliquot, and then it's poured into the conical flask at the bottom of the titration, ready for analysis. So in this one, we would have sodium carbonate at the top in the burette. Now the standard solution, in this case sodium carbonate for example, is placed in a burette which delivers accurately known but variable volumes of solution. So the volume of liquid delivered by a burette is called a titer. Now have a look at the right hand picture, the burette containing standardized solution of sodium hydroxide with a known concentration. It's going to be the volume that changes, isn't it? So once the titration is complete, the volume is also known because you can measure how far it drops down, and that's therefore a known volume. This information can then be used to calculate the concentration of hydrochloric acid in the conical flask. So we know the concentration, we know the volume here, and we know down here we know the volume, but we don't know the concentration, and that's what we're going to determine. So the conical flask containing hydrochloric acid of unknown concentration but of known volume. So we just use an indicator is added to show the endpoint of the titration. So remember, we want that endpoint to match the equivalence point, so we know when the equation is balanced or when they're in stoichiometric ratios. So a couple of the other equipment. So we have a suction bulb on a pipette for safe pipetting. Beakers you should be familiar with. Burette is used for accurate volume measuring and titrations. Conical flask, also known as an Erlenmeyer flask. Now we have this graduated volumetric flask. It's used for measuring liquids and preparing and manipulating solutions. We have a calibration mark. Remember, the bottom of the meniscus of the solution should hit that calibration mark, and a measuring cylinder If we do have issues with measuring, we can always calibrate by weight. Okay, in titration, you're going to be dropping a certain volume until you hit an end point. And so this is going to be a volume measurement. Now, to measure the volume in the burette, you can see that the scale increases from down here to here. And this would have to be 19.5 here, wouldn't it? So we're going to have to create measure this, sorry. So you know that this is 19.4. It's not quite 19.4, but it's certainly over 19.3. So we are certain that this is at least 19.3. What we will do then is just round off in this case, because it's not quite hitting the 19.4, so we'll just call it 19.38. So we have a certain and an uncertain value here. So the burette is read from the bottom of the meniscus, and the volume is estimated to the second decimal place. So the volume measurement in this case is 19.38. So this calibration is what, 2.10 of a mil. The uncertainty is generally 0.05, which is generally half the smallest division. Now, to minimize errors, when we do this, your first titration is just going to be an approximation. So you will probably overshoot. And so that's okay, because you just want to get a round amount. So in this case, we have a look here. It started off at 0, and we put in 20.2 mils. Now, so we know that the end point has got to be a little bit less than 20.2. So on the second titration, you'll let down about 19 mils very quickly, and then you'll do it drop-wise from 19 until you hit that end point, stirring as you go until you hit the end point, or swirling that flask. Now, what we want to do is find 3 concordant titers. So they need to be within 0.1 of a mil. So remember, our calibration is that. So it's just to the level of uncertainty. And let's have a look. 19.8, 19.64, 19.78, and 19.86. So we just find the 3 concordants, and what do? We take the average. So it's got to be this one, and this one that we use, because this one is not concordant and this one is our estimation. So if we were to perform a simple titration calculation, so we've got a 20 ml aliquot of hydrochloric acid, and it was titrated with 1 molar solution of potassium hydroxide. So we've got titers of 25.03, 22.10, 22.05, and 23 and 22 were required to reach the endpoint. So calculate the concentration of hydrochloric acid. So first of all, just construct the full balanced equation. Then you find 3 concordant titers. So remember, they've got to be within 0.10 mils of each other. So this is what we're doing here. So 22.10, and then we've got 22.05 and 22. So they are the 3 concordants. Remember, that's an estimation and that's not concordant. So once we have that, we take the mean of those 3 concordant titers and use that for our volume. So now we know a concentration and we know the volume. So we can work out, using C equals N on V, the number of moles being dropped of potassium hydroxide. And so that's going to be 0.02205 moles. Now the mole ratio is 1 to 1. So however many moles of potassium hydroxide, we're going to have the same amount of moles of hydrochloric acid. And so that's what we're seeing here. And finally, we can work out the concentration of hydrochloric acid by manipulating the formula C equals N on V, by using it, sorry. And so we have a 0.1 1025 molar solution. Now, you can use this formula, just be careful of it, C1V1 equals C2V2, and it will work when the mole ratio is 1 to 1. But you will have to manipulate it otherwise, or take into consideration the mole ratio if you're going to use this one. So I wouldn't recommend this one unless you're really confident in knowing what you're doing. Now, sometimes you need to dilute one of your solutions. For example, if you want to calculate the concentration of an acid or a base in a cleaning product. So, for example, Drano has a lot of sodium hydroxide in it. And in this case, we've got a 50 ml volume of cleaner, of maybe Drano, for example, and it's diluted to 250 mils. So it's 50 mils in the bottom of a volumetric flask, diluted and measured up to 250 mils, so just 200 mils of water added. Now this was titrated against 20 mil aliquot of half molar hydrochloric acid, and that was placed in the conical flask down below. So in this case, we've got a known concentration and a known volume. Sometimes it depends on your style, whether we're going to have a look at the concentration being known either upstairs or downstairs. So in this case, we don't know the concentration of the base being dropped. And we've got the average titer being 18.56 mils. Okay, so what we want to do is calculate the volume of sodium hydroxide in the cleaner. So what we'll need to do is just find a full balanced equation, and so we've just got 1 mole of HCl and 1 mole of NaOH. Now let's determine the number of moles in what's known. So what do we know? We know A, 20 mil and half molar, so yeah, so that's our volume and that is our concentration, so we'll use that one down below. And what have a look, we always place it in a conical flask down below in this case, and the average titer, so in this case we're dropping the sodium hydroxide or the diluted solution of Drano, and we need to find the concentration of the sodium hydroxide in the Drano. So what we want to do is, okay, here's our half a molar of hydrochloric acid and 20 mils hydrochloric acid, and we can work out the number of moles, N equals CV, so we're just multiplying that to get 0.01 moles of HCl. Now the average titer for the sodium hydroxide was 0.01856 litres. Now we have a mole ratio of 1 to 1. So if we have this many moles of HCl, we're going to have the same amount of moles of sodium hydroxide. So we now know the number of moles of sodium hydroxide. We know the volume of sodium hydroxide. From there we can work out the concentration. C equals N on V. So the number of moles in the diluted solution of sodium hydroxide is 0.53 moles per litre. Now we just need to think about this dilution factor again. Now it's 250 mils divided by 50, so that's a dilution factor of 5. So we just get this number here from our diluted factor, a diluted solution, and we multiply it by 5, which is a dilution factor, to get 2.69 moles per litre. Now remember, everything that we do will have some error and uncertainty associated with it. So we do aim to be precise and accurate in our measurements. Generally speaking, your uncertainty is half the smallest division if it's not displayed on the equipment. So here's our level of uncertainty here for this volumetric flask. So remember, that's when we fill that up to that calibration line there. If not stated, so it's half the smallest division if not stated on the equipment, or it's on digital equipment such as the digital balancers, is going to be the smallest decimal displayed. Mistakes are those avoidable errors. So if you're misreading numbers on a scale, if you spill some, if you use the wrong pipette to measure the volume, or if you incorrectly rinse the glassware. Now, if you have any calculations or measurements that involves a mistake, you must reject that and can't include that in your calculations. So some of the rinsing procedures are important. So the correct way to rinse a burette and a pipette is the final rinse of the burette or pipette should be with the acid or base that they're about to be filled with. If we do it with water, you're going to dilute it, and your first one will not be as accurate, will it? So we want to do our final rinse with the acid or base that you're dropping in the burette, for example. If the incorrect way is to, rinse with water. There we go. So the other way to, the correct way of rinsing a volumetric flask or a titration flask or a conical flask should only be rinsed with the deionized water. If you rinse with acidic or basic solutions, you'll introduce unmeasured amounts of acids or bases into the flask, and that will affect results. There are two sorts of errors that you'll come across as well. Systematic errors, they produce a constant bias, and they generally fall into two categories. One due to the equipment. So, for example, faulty equipment, it might be as simple as a bubble in a thermometer. That will always give an extra reading, for example, or a poorly calibrated equipment, or poor experimental procedures. So they're things that are going to be systematic. They're going to happen again and again. And random errors are going to follow no regular pattern. We've done a bit today, and we should be ready for our mandatory practical very soon. But first of all, I'd like you to have a go at the mastery exercises, please.